I'm very happy. I'm very happy to introduce the first speaker of today, who is actually also a visitor in sabbatical for this year at the CfA, and is Endre Takacs. He earned his PhD in atomic physics from the University of Debrecen in Hungary. He's currently a professor at the Department of Physics and Astronomy at Clemson University. His research interests include atomic physics in highly charged ions, including their application to fundamental physics problems, atomic processes in high temperature plasma, laboratory astrophysics, and also medical physics application of radiation. Endre is engaged in various academic and research activities globally, including positions at University of Debrecen, Oxford University, National Institute of Standards and Technology, MIT, Vanderbilt University, and Queen's University in Belfast. And also, in addition to his academic pursuits, Endre has contributed to various medical and radiation physics consulting projects. And today he's going to talk us about collapse of a sympathetically cooled cloud of strongly interacting highly charged ions in an EBIT. Thank you.
Thank you so much, Federico, and thank you for the invitation as well to be able to present you this talk. When I was thinking about what would be the most appropriate data to present to you, I thought that I dig back to some of our old results, as old as like 20 years old, and it was only published in a very obscure conference proceedings. But I thought that this would be an appropriate kind of like introduction to what we are doing with our electron beam ion traps. And also kind of like a little bit away from the mainstream light identification work that usually electron beam ion trap research is known for. This data was taken with some of my former students, and the then group leader of John Gillespie, who is at the National Science Foundation right now, is the program director of the AMO program there. Maybe do, yeah, do. Sorry. Okay, great. Thank you so much. I know that this is a nice anniversary here at SAO. 25 years ago, there was the launch of Chandra. And we celebrated that at that time when we were doing measurements at the NIST electron beam ion trap. But we are also celebrating the also 25th anniversary of the first EBIT X-ray microcalorimeter, but and that was also built by SAO. This was a first instrument X-ray microcalorimeter similar to the new advanced astrophysical missions that are currently planned, or the CRISM that is up there already. And the calorimeter only had 4 pixels, 2 was working out of them occasionally, but it also had a very nice feature, an X-ray telescope that only could have come from SAO. When we first complained that these tiny pixels are probably going to be like way far away from the source, we were told by Herb Schnapper, whose hand you can see here, and who was a collaborator at that time, well, this is what we do at SAO. We just look at like faint sources, so don't worry about the faintness. We'll make it work. So they designed this nice X-ray telescope. It was put in between the source and the calorimeter, and it worked like a charm. Now, 25 years later, the NIST electron beam ion trap is still operational, but there is one at SAO now, and that Amy has put together, and I'm spending my sabbatical to try to do spectroscopy on this nice little device that you have here. There are some differences. The NIST one is a vertical device. This one is a horizontal one. and there are different instruments on it, but otherwise the operation principle is the same. So what is the operation principle of an electron beam ion trap? I would like to maybe kind of like make a comparison with the kind of sources that you are looking at. We actually have a jet of electrons shooting upwards in our machine, compressed by a magnetic field of swarming electrons, and those electrons are representing a current in a superconducting magnet. The magnetic field is about 3 Tesla. That compresses this beam or jet of electrons to about the thickness of a human hair and to densities of about 10 to the 11, 10 to the 12 electrons per cubic centimeter. The electrons are unique in a sense that they are monoenergetic. Their energy is determined by the potential difference between the electron beam and the middle of the trap. So that creates a unique condition inside the trap region where we inject some neutral gases from one of these side ports that interact with this jet and light up. Similarly, that these material light up of the interstellar medium light up as a jet passes through it. In our EBIT, as the electron beam passes through this neutral region, it lights up those atoms. But we have an additional constraint in our EBIT. This inner trap region is segmented into 3 regions. So we can apply an axial trap to the machine. And as a result, we can confine the ions that are created in the interaction and then further ionize them. And they can reach to really high charge states. We can basically produce charge states, every charge state of every element of the periodic table with different versions of this device. In the NIST one and in the SAO one, I would say we can produce about 90% of the charge states of all the elements of the universe. We are using devices similar to your telescopes to observe these clouds. And in our case, this was a nice, simple, visible spectrometer, a Chan-Eternal spectrograph, and we observed ions that were injected into the EBIT. And in this particular measurement that I would like to talk about, we injected a mixture of argon and xenon ions into the EBIT for reasons that I'm going to talk about shortly. And we observed emission from these highly charged ions in the spectral range that we were sensitive to with our spectrometer. We actually observed famous visible light emitted. This was a transition in titanium-like xenon. It's famous because this was the first visible transition ever observed in an electron beam ion trap. And we observed another famous transition in boron-like argon. This transition later on was measured to extreme precision, and the first highly charged ion-based atomic clock is based on this argon 13 plus transition, and its wavelength as a result is known to 1 part in 10 to the 16 accuracy right now. It's one of the most precise transitions, atomic transitions, and it is the most precise highly charged ion transition today. So our experiment was kind of like a follow-up of a previous work where the cloud was imaged. This is the visible image of the fluorescence image of the electron beam passing through this highly charged ion cloud. And then in that work, the conditions of the ion clouds were changed by changing the axial trapping potential, making the trap deeper or shallower, and as a result, changing the temperature of the ion cloud. Both of these transitions are metastable transitions. They have lifetimes on the order of milliseconds. And that's enough time for these ions to basically sample the whole ion cloud. And they actually wander outside the electron beam as well, and they light up the whole ion cloud distribution. Now, if you change the depth of the trap, you change the temperature of the ion cloud, and you see the fluorescence signal, the intensity, and the width of the ion cloud changed. The width is determined by the Boltzmann distribution in the potential of the electron beam axially, and this potential difference that we apply. We apply axially, and the potential by the electron beam itself radially. The ion cloud itself is in thermal equilibrium, but is not in thermal equilibrium with the electron beam itself, which is a monoenergetic electron beam just passing through this cloud of ions. So in our follow-up experiment, what we tried, we injected an argon-xenon mixture of gases. The main reason for this was because we wanted to see how these two ion species interact with each other thermally. What is the thermodynamics of these two species in the trap at the same time? Because argon is a fairly light element, xenon is a heavy element. So as a result, argon ions can actually cool the xenon ions. It's a process called sympathetic cooling, and it's by evaporation. You lose argon ions in the process, but at the same time that the large, heavy xenon ions cool in the process. There's another property of these ions that I need to mention, and that is their charge. So our electron beam was at a monochromatic 2000 electron volt energy. And so if you bombard these ions with 2000 volt electrons, they reach different charge states. And the reason being is because on this graph, you see the ionization potential of these two species. This is xenon. This is how much energy is required to remove an additional electron from xenon atoms. And it goes up like fairly shallow, and then you see the shells, and then the last two electrons to remove, you need more than 40,000 electron volts. Now for argon, the curve is much steeper. So when you just bombard them with a monochromatic energy electron beam, the argon ions reach lower charge states than the xenon ions. So as a result, the trap, the same potential that you apply, is much deeper for xenon ions because of their higher charge. The trap depth is the potential times the charge. And so this is interesting because you can trap these xenon ions, but you can also control the cooling of these ions by changing the trap depth, which is much shallower for argon atoms. So what did we see? Basically, we observed the same kind of images. And on these graphs, you see as we change the trapping voltage, make the voltage shallower and shallower, we observe the intensity, the total intensity of the ion cloud. And as we expected, the argon signal were just dropping. As we were losing argon ions, the trap is shallower, it can contain less number of ions. So this was kind of like what we expected actually for both pieces. There's an additional caveat here because you see here that the trap depth is actually going into the opposite direction. So we need to move the trap depth into the positive direction to remove all the ions. And the reason is the space charge of the electron beam itself. And so for argon ions, this did not really change anything. We were losing them. But for xenon, and at these very shallow trap depth, we observed something that we couldn't really understand at that time. And I like to say that maybe we don't even understand it right now. We saw a tremendous increase of the intensity of those few xenon ions that remained in the trap. In the matter of a few volts of trap depth, the signal shoot up to really high, comparable to the intensity when the trap was full, and probably hundreds or 1,000 times more xenon ions were in the trap. So this was puzzling. So we had to do some more investigations. So we looked at the, I'm sorry for, yeah, so we did a little bit more investigation. We actually looked at the width of the ion cloud itself. For argon, there was nothing really dramatic that happened. The width of the ion cloud shrunk as the ions got colder and we had less number of them. But for xenon, for this 32 plus ion, you saw a big dip of the size of the ion cloud as well. So if you recall what I said about the size of the ion cloud, that it's basically the Boltzmann distribution that depends on the potential and the temperature of the ion cloud. This is probably a suggestion that the temperature of the cloud drops dramatically over a very narrow region. And so that made us think, if this is some kind of a phase transition that might be taking place with these ions. So we dug up some literature about non-neutral plasmas, plasmas of a single sign of charge. And indeed, it turns out that the thermal equilibrium state of the plasma is determined by this parameter, which is the so-called Coulomb coupling parameter, which tells you the ratio of the potential between nearest neighbors and the kinetic energy that each ion has. Obviously, if this parameter is very large, then the potential energy due to the next neighbor is very large. So there's no kinetic energy for the ion to hop over the next one. So in the extreme case, you can actually create a so-called Coulomb crystal that was observed since then, when you can cool your ion cloud to low temperatures. And this was indeed predicted for gamma larger than about 170. There is a phase transition to a crystal state. And in fact, the precision clock that I mentioned uses that cooling process, and they do observe those crystalline states of these argon ions. Now, in our case, probably we are not in that regime. We cannot cool our ions because they are constantly bombarded by the electron beam. So there's a constant heating of the beam itself. But this very efficient sympathetic cooling by the lower charge state argon ions, we kind of like to say that we might be reaching an interesting regime where some kind of a collective effect might take place. Maybe it's a phase transition, kind of like a liquid-like case, some fluid behavior that can be observed. We don't really know what the temperature is of our cloud. Probably we could speculate on that by looking at the width of this of the cloud. But if we are putting it into this regime, I might argue that it could be in this high Coulomb coupling parameter regime already, where we might be able to observe some collective behavior. So why did I decide that I should present you this for this audience? I think there is a discussion whether these strongly coupled plasmas are present in different astrophysical environments. So this is a plot that I borrowed from the Lawrence Livermore dense plasma theory group. And they actually point out that the conditions for ion clouds having some collective effects in different objects might be in this regime. Newton star crust, white dwarf, even like the Earth core might be in this regime where these collective effects can be observed and need to be accounted for. So, if you encounter such a scenario, just think about our little machine, the electron beam ion trap at the Discovery Park. We might be able to do some modeling and some experiments for you to explore this interesting regime. And so this is my summary. Our electron beam ion traps are mainly used for spectroscopy. Now we have one at SAO as well. Ions are created by an electron beam compressed by a superconducting magnet. Metastable ions emit throughout the ion cloud, so we can study both the electron beam and the ion cloud itself. And this decrease of the size of the sympathetically cooled xenon cloud might actually provide us a first case of a strongly coupled collectively behaving plasma in our device. With this, thank you.
Okay, we have time for questions.
So I'm confused. I can understand that it becomes strongly coupled and that collective behavior, but why inherently would that become much brighter? I mean, what's creating the enhanced emission inside that strongly coupled plasma?
Right. So what we believe is happening is that maybe there is a show up of some collective behavior, and that puts that cloud through the threshold of some kind of a phase transition where the temperature drastically drops. And so the whole ion cloud just drops into the center of the electron beam, becomes very narrow. We do observe the and then there is a higher density for the electron beam. Our density profile is usually assumed as a Gaussian profile. So the middle of the electron beam has a lot higher density than the outskirts of the electron beam. And so that's what we kind of like speculate that with this collapse of the cloud, it sees a higher density electron beam, and that lights up the atoms.
And the density enhancement in the bottom of that Gaussian is large enough that it would explain the emission enhancement.
Right now, we are just speculating on that. We need to model this. At that time, we thought that this was like a cool observation. We presented it at a new neutral plasma conference. We were told that our plasma is not interesting because it's not a non-neutral plasma because we have electrons. We tried to convince them that, well, the electron beam is not in thermal equilibrium with our cloud, but they have, other nice businesses like Coulomb crystals to deal with. So we are just trying to kind of like connect with the right people. And I think, after 20 years, there was enough development of this theory that they think that those regions which are not, the crystalline regions, but these fluid regions, which might be very important in, for example, astrophysical plasmas, where, you have like a low charge state something or a neutral material swirling into the accretion disk, and down here it could be like fully ionized or even become like quantum collective, become a neutral star. So in this regime, this could actually play a role.
Thank you. More questions?
In some EBIT, they change this trap depth and that changes the energy distribution of the electron beam, right?
Yes.
Do you think that had some effect on this?
Yes, that's also a possibility that because the potential itself that play a role here is not just the potential of the electron beam itself, is the combination of the electron beam and the ion cloud. So it is a self-consistent potential due to both species. So that's one of the complications, how to model that, and what is our real potential. But I agree that, the change of the potential might have played some role in this too. Yeah.
Any more questions? Feelings? Okay, so if not, let's thank Endre again. Speaker.
So our next speaker is Gunderson, who is currently a postdoc at the MIT. Sean earned his PhD at the University of Iowa after his bachelor's degree from North Dakota State University. For his PhD, he developed two line profile models for the X-ray spectral lines from hot stars. The first of these models approaches the problem of hot star wind shocks as originating from surface variabilities like in the sun, rather than from inherent line driving instabilities. The second model approached the problem by adapting an analytic solution to Herbig Hair jets for application in accelerating flows. He also made the first identification of X-ray dielectronic satellite lines in a single hot star and used them to show that collisional ionization equilibrium is reached in the shocked plasma. His general research interests are in the stellar astrophysics with a focus on hot stars of OB and Wolf-Rayet types. His current research interests include X-ray analysis of gamma-K stars and multi-wavelength analysis of hot stars. Today, Sean will talk about zeta puffs, surprising variability. So the floor is yours.
All right. So yeah, the main thing I want to talk about is zeta pup and what might be some strong variability in it that's kind of surprising. And it could be because it's losing more mass. So the first thing to mention is what properties does zeta pup have as our prototypical hot massive star? Well, it is an O4 supergiant, so it's really bright, really close, and really hot. It's at the 40 kilokelvin point, though some of these properties are dependent on its distance that we're not fully aware of to the best of our ability. The Hipparchus data says like 330 parsecs, so these are it looks like the lower boundaries seem to be the right values for this. Now, what I show on the left is an artist rendition of some work that possibly shows that zeta pup has some bright spots on it, almost like you would see on the sun, which is not what we expected in hot stars, because there's just supposed to be smooth balls of gas that are leaking off material, not active like solar-like stars. So the most spectacular difference between a hot star and a sun-like star isn't in these properties directly. I mean, obviously it's huge compared to the sun and it's a lot hotter, but what the main difference comes in their stellar winds. So here's a nice graphic from JPL showing the scaling of the solar wind to the rest of the planets. And going about 400 kilometers per second at the termination shock, it's only about 100 AU wide in radius. It's not very big, doesn't lose that much mass. It's 10 to the minus 14 solar masses a year. But when you scale everything up to a hot star, everything just goes to a completely different scale. This is the Bubble Nebula seen in optical. I believe it's a Hubble image. Do not quote me on that. But you can see how big this gets. This source star right here has made a bubble that's 4 light years in radius. And the wind is also traveling much faster. These get up to about 2,000 kilometers per second and carry a lot more mass in them. They characteristically 10 to the minus 7 solar masses a year. So there's a lot of momentum in these. And it's kind of hard to get these going if you just think of them like a normal solar-like wind. So, for example, in the sun, if we write down the momentum equation from plasma physics, you just have gravity and a simple term of how pressure is changing with radius. And for the sun, you go from about 1,000,000 degrees in the corona and 10 to the minus 9 particles per cubic centimeter to out by the Earth, you've dropped by an order of magnitude in temperature and a huge drop in the amount of particles. So you get pressure gradients that just naturally let the wind flow outward as they need to satisfy the boundary conditions. But now think about trying to do this for something that needs to go 2,000 kilometers per second and carry 10 million times as much mass. It's kind of hard to think about how that works. Well, in some really influential papers back in the day, I think it's like the 60s and 70s is when this started, you started to see radiation hydrodynamics come into play, where we're going to start coupling radiation into the momentum and energy equations and see what comes out of it. And you might notice that now there's still gravity. It's a little weaker because we have to account for radiation puffing up the atmosphere. But you also don't have the pressure gradients anymore. Now we have this G radiation, an acceleration due to that radiation. And in the simplest case, it's much, much greater than any pressure gradients you can get just naturally from expansion. In fact, you can start off just by fairly easily showing that the radiation acceleration is 2,000 times that of gravity. So it's really easy for the radiation from these stars, because they're so big and so bright, to just blow off the wind, no problem. So I always like to explain this to people that it's essentially a solar sail, that it's the same process, but actualized in nature, but this takes a lot more energy to do it than, just from a solar-like star to be able to do this. These stars are so hot that they're mostly in the ultraviolet, and so they're mostly pushing on metals when they do this. If we go a little further and sort of like where's the state of this radiation hydrodynamic work, we tend to parameterize hot stars' velocity with what's known as the beta velocity law. It kind of comes out naturally from the basic differential equations. Well, I say basic for hydrodynamics, but it kind of comes out. It's not actually there, but this form really is what works the best to match both simulations and our observations. Beta is generally taken to be 1 for keeping things analytic, but if you fit data, it comes out to about 1. Maybe it's like 3/4, but generally it's about 1. And terminal velocities are about 1,500 to 3,000 kilometers per second. So it works pretty well, and you can see in the way that in the beta law that it accelerates very quickly. We get to 1,000 kilometers per second within a couple stellar radii off the surface. So it's not hard to get up to the speeds. It's just you have to use a different method to get it. But you might have noticed that 2,000 times gravity was a huge number, and there might be some problems with that if suddenly you're pushing stuff off much faster than gravity can hold it back down. Well, there's an easy fix for this just in the amount of material that's in the winds. So let's now take a case where, let's say we have just a single atom farther out from the star and another one between the outer atom and the star itself. In this situation, the outer atom won't get all of the light from the host star. It's going to get a reduced amount because this one is shadowing it. And this effect naturally occurring in the winds, especially as you go from looking at atoms and atoms to clumps of gas, causes a self-shadowing effect where the ions regulate themselves to only about accelerating to 2 times that of gravity. It's still enough to blow the wind, but it's not enough that we're ripping an atmosphere off the star every second. So what's really interesting about this is that this self-shadowing causes a regulation in the mass loss rate of the star. Because if you put too little mass in the wind, just in our heads, think about putting too little mass there, there's too much flux from the star, so it can push on more things and fill up the wind, put it back into some optimal value. But now imagine if that went too far. You kept pushing and pushing and pushing, and now suddenly there's too much mass and it can't flow as well. Well, in that case, you're going to lower the amount of mass you can keep pushing on and go back down to this optimal stellar mass loss rate. So in comparison to the solar wind, where you have any mass loss rate can fit any amount of flow outward because it's just a pressure gradient expression, here, only one mass loss rate really will fit the physics that's occurring, because if you put too much or too little, it just puts itself back into that location. There's possibility of this being variable, which I'll get to in a second, but the historic theory really says that there's one mass loss rate, and that's the only one that that star can support. Now, the important thing with these this self-shadowing is that it doesn't go away. Just because it can help regulate the inner boundary and how much mass you're blowing off, doesn't mean it's just going to suddenly disappear, because it will always be present at every radius of the wind. So while it stabilizes the flow through the sonic point, shown in this 2D simulation down here, it will disrupt the flow and destabilize it after the sonic point. Because let's say you have tiny little density fluctuations for one reason or another. It could just be a small sound wave that occurs in this. It's going to grab onto those tiny fluctuations and amplify them. Anything that is a little overdense will become more dense as stuff piles up behind it. And anything that's not dense enough will just get pushed forward. And the result of this is that you can get hypersonic shocks. The instability here is known as the line deshadowing instability. There's a little bit more that goes into why it's called a deshadowing. But eventually, far enough out, you get some pretty strong bow shocks that form characteristically about half a stellar radius or to 1.5 stellar radii off the surface. Depends on how your simulation is set up. But there's some lag time before this occurs. And this is our current theory to explain the X-rays we see from these stars. They weren't expected to have X-rays before some of this work came out, but they surprisingly did, and this really helped to explain them without having to make any contrived models to make it work. So what do the X-rays from these look like? Well, here are our 4 prototypical O stars that are non-binary and cover a okay range of spectral types. And specifically, this is the Chandra Meg data that has been de-reddened to make it look a little nicer from a paper by Oskanova et al. But we can see that we get about 0.5 to 3 keV energies in the line emission. They're primarily thermal in their thermal metal line emission because there's very little continuum between them, so it's not too hot. But the lines do need about 10 megakelvin temperatures to see the ratios and the emission that we see in and of itself. But if we focus in on each individual line, we can see that they are blue shifted generally to about 1/10 of the terminal velocity, but they're also broadened with a full width half max of about the terminal velocity. So you can see some of this radiation driving already showing up when you measure the lines in and of themselves. In fact, I believe it was Zeta Oph or Zeta Ori were the first O stars measured with Chandra, and it was a slam dunk explanation for the embedded wind shock model, just because it fit what we knew from theory right away. But there's some challenges to this more recently, because Zeta Pup, again, some of the brightest, easiest to observe O stars, had a recent some recent observations in cycle 19 of Chandra that show some changes. Some of this is due to Chandra's degradation, such as down in this region. But over in the less than 10 angstrom region, some of the lines look different. It's hard to show in just like one plot how different they are, but there are measurable differences. So really, what's going on? Well, the first thing to note is that the theory work hasn't stopped with some of this radiation stuff. We've actually created line profiles from this basic theory. I'm not going to go through all of this equation because that would take in and of itself an entire talk. But the Cohen model, as I like to call it, from its original author, made a line profile model that inherently respects the basic physics and is able to fit these lines and actually get out from the parameters the mass loss rate. Because if you know the terms such as the opacity, the radius, and the terminal velocity, you can get a free parameter to fit to a bunch of line fits to get out the mass loss rate, which is what Cohen did in a recent paper in 2020, where comparing the original cycle 1 data to the cycle 19 data from ZetaPub found a 40% increase in its mass loss rate in 20 years, which is pretty spectacular because we're already talking about millions of solar masses coming off this star, but now you're gonna almost double it in effect. So there's a lot of questions here of what is going on. So the first thing to really understand is this method right? Can we do this? Can we get mass loss rates from this model independently and not have to worry that maybe there's some problem with Cohen's approach? And for that, we just need a line profile model that fits the basic, we have a source term and we have a term for extinction as photons travel through the wind, because the shocks are within the wind, so they'll get attenuated by later stuff that never shocked. Well, the first step to do that is to note that some more recent simulations on the LDI and these winds have shown that it may not be the dominant mechanism to generate these shocks. In a more recent a separate simulation in 2015, where the authors, Owaki and Sundquist, added in scattering into their radiation modeling, actually found that these strong variabilities are occurring right away at the surface, and they're not taking any lag time to get there. So it might be, depending on what, if you think their methodology was correct, that these shocks can actually occur much sooner than we thought. It may not take a lot of time for them to form. They're just going to happen as fast as they need to based on the radiation driving that's applying to them. And this was what I used to generate to derive a new line profile model, just based on this idea that if two simulations are able to match what we some of our observations, they should be able to also generate line profiles that fit the data. So again, it's an integral I'm not going to go through because it would take too much time. But in my model, I followed the same principle that there's an extinction term and a source term. But importantly, I have a different radial component here, not talking about the length of time or how much space there is before shock occurs, but just some characteristic mean free path between shocks. Just how much space is there characteristically between them, generating sort of a turn-off radius. It's not fully turn off, but you can expect most of the shocks to have occurred after the mean free path. And the first thing is that I can note is how well my model can fit the data, just like Cohen's did. So that clears the first bar of, okay, I can fit the data equally as well. What that means in X-ray can mean different things in optical, but it fits it consistently. The second thing I can note is that if I compare my model fits to the cycle 1 and cycle 19 data, which are the blue and orange points in this plot, to the Cohen cycle 1 and Cohen cycle 19 values in green and red, it's a little busy, but you can note that they're all pretty much consistent throughout this. In fact, my two data points and the green ones from cycle 1 from Cohen's work are statistically the same in pretty much all of these. There's a couple that they're not that could come down to systematic errors. But Cohen's 2020 paper is not consistent in this. Something is different from using his model in the more recent data to my model in both data sets. And what I think the problem is how much of the profile he fit for such as this neon line right here. So this is neon 10 hydrogen alpha like emission. And for my model, I fit from the blue wing to the red wing fully as best I could. Cohen, though, didn't fit all the way down into the red wing of this profile, and that may have skewed his results. That's my personal opinion at the moment. I'm still doing some work to actually figure out the systematics of, like, what happens if you fit half the profile to 3/4 to the full thing, but that looks to be the only explanation I can come up with when everything up to this point has been near identical. So if the mass loss rate in Zeta Pup didn't change, what did? Because I still got to explain why the data looks different. And the way I would explain this is that the spatial parameters have changed. So in this plot, what I show in blue and orange is that turnoff radius in stellar radii R star plus L naught, or in stellar radii 1 plus L naught. And in green and red, Cohen's R naught, his turn on radius at which X-ray shocks would have occurred and started emitting. And for Cohen's model, doesn't seem to have changed much. Maybe there's a little bit of increase in some of the lines, but you could fit a straight line between these and be equally fine in both of them, partially because of error bars, but also partially because of scatter. In my data points, though, there's been a consistent increase across the lines. It's a little harder in some of the later lines, which could be due to the degradation on Chandra. But overall, there's been a net increase in my mean free path parameter. So it's almost as if the distribution of the shocks has changed, that there's more space between them and they're getting out to farther radii, and maybe that's why we're seeing the changes in the profiles. But how to explain that from the stellar perspective of why is really hard, because it doesn't, as far as I know in optical, it hasn't changed. And I think the last time it was looked at in UV was before the Chandra data, so it's hard to know if the UV flux has changed. But clearly something has, because two different models are telling us that something has truly changed. So I can come up with a nice conclusion that from my data and modeling, that for one, X-rays are dependent on your fitting process of the lines. You can't just say, I'm only going to fit 3/4 of the profile and get a mass loss rate out of that, and that should be fine. No, the wings are important. Even if we can't resolve the wings due to our detector resolution, they still are important to actually get a proper value. But the good news is that it can be independent of the model you use. Because in with two different models on the same data set, I get the same mass loss rates, assuming you fix some of the problems of how much of a line profile you fit in and of itself. Now, from my model, I would argue that Zeta Pup's mass loss rate has not changed, which is good, because trying to explain why suddenly there's 40% more mass in the wind is going to have a huge effect on the changes to the local interstellar medium, the evolution of Zeta Pup as a star, and we may have to question if we need to look at more of these O stars more frequently to understand if all of them are going through such a process or if it's something unique to Zeta Pup. But there is still a change. Maybe it's the radial distribution of shocks, but I have to agree that something's different. So maybe Zeta Pup's variable. Perhaps there are stellar cycles in it, just like a cool star, where maybe something changes with its radiation output and changes the shock distribution. I don't know from this one data set, but I have a collaboration that I'm heading that I call the Joint All Wavelength Analysis of Zeta Pup, or JAWAS for short, where what my goal is to connect features across wavelengths and epochs, getting every single data set possible that's public on Zeta Pup and say what similarities are there over time and within observations. Because these things are correlated. we know from other works that the UV can be connected to the X-ray with some lag time in the driving. The optical should correspond due to recombination of helium-like ions in the wind. So all of these pieces are interconnected, and at this point, we might need to do a full radio through X-ray analysis to understand and piece this stuff together. Now, for the data sets that I have so far, there's XMM and Chandra data on Zeta Pup. I believe there's also nicer data I'm gonna have to double check on. There's archival IUE, EUVE, and Hubble data, and there's optical and infrared as well. But the key piece that really is driving home how different Zeta Pup is XMM's PN camera flux measurements. This is a little old. I need to update this with the newest observations from XMM, but in about 5 years, it had a 20% increase in its X-ray flux, which is really saying that there is something different in its X-rays generation mechanism and the way that its line driving is occurring. So unless this is a problem with XMM's calibration, which I'm talking to someone from their calibration crew about, it's really saying that something's different in Zeta Pup, and maybe O-stars are not as boring and smooth of objects as we once thought.
Rito, questions?
So maybe I missed, have you measured the wind properties for the star, like the actual speed and the wind velocity and the density?
So density is really hard as a property to measure due to the clumping of the winds that comes out from the line deshadowing. But you can get terminal velocity measurements from the broadening in the of the lines. So let me go back, get a better. So if you just fit this with a Gaussian, because they're pretty Gaussian in shape and it can fit it well, the width of that Gaussian is usually about the terminal velocity, at least the full width half max is. And that's generally how we get in X-rays the terminal velocity of these stars.
So what is the
In Zeta Pup, it's like somewhere between 2,250 to 2,500. It's some more recent measurements push it higher, but it's not clear which one's right. You can also get it in the ultraviolet, but there you get a problem again with like the density being if you've actually measured that correctly.
Can you go a second to the plot showing the shocks coming from a very region? Yeah.
Actually,
Yeah.
this will work.
Yeah, so I was not clear. Where do you think one could locate the sonic point? Because from what I see, the shock comes from very close to the star surface, right?
Well, it depends on if you're talking about just a shock and a X-ray generating shock. Because in the LDI framework, down here, there's some shocks occurring, but they're not strong enough yet. Because you need time for the wind to accelerate to get up to speed the 1,000 kilometer per second shock speeds that we need. That is a good point. That where is close enough? And it's really about the strength of the shock more than its raw location.
But these could be just discontinuities, steepening, not necessarily shocks. So.
Yeah, because it's sort of like the clumps are building up and building up and building up as they accelerate.
Okay, makes sense. Thanks.
There's a question in the back corner.
Thanks, Hawk. So I was wondering, so you mentioned that in these radiation-driven winds, they primarily act on the heavier elements in the wind.
Yep.
Does that require like high densities, high number densities then? And
Oddly enough, no. It's really the metals that are doing the they're mostly being pushed on. And you can have a small amount of metals and still get the same effect because they have a lot of absorption lines. In a similar, it's not the exact case, but if you think about iron, as you go up to like 200 kilokelvin, iron suddenly blows up in its opacity. And it gets tens of thousands of absorption lines. So if you scale that temperature down, and now you're looking at things like oxygen, carbon, nitrogen, silicon, things like that, and you're at 40 kilokelvin, you're still at a high absorption level, and there's a lot of UV lines that can be pushed on, effectively creating a blanket of stuff to push on, even if they're a small actual number fraction of the particles in the wind.
Any more questions?
Have you considered weak wind O-stars?
So
They're an interesting class. They're typically main sequencer subgiants.
yes.
So they're very different from Zeta Pub.
So weak winds, oddly enough, are kind of normal in the X-ray. And my postdoc advisor, David Hunemorter, in 2015, I believe, on mu cold data, showed that the winds are still just as dense, but they're just not cooling. I shouldn't say they're just as dense. They're accelerating just as you would think for like Zeta Pup is, but they're not dense enough to cool fast enough, so they stay hot, and that's why they look weak in the UV, which is where their designation is traditionally coming from.
So not weak in MDOT.
Yeah, not weak in MDOT, just they may be a little lower MDOT just because they're not as dense, but it's sort of a archaic term from when we only knew about them from the ultraviolet.
Thank you.
Any more questions?
Sorry, one thing I forgot to ask. So it's convenient that we are still on this slide. What's the units of the y-axis here in kiloseconds?
So the y-axis is the stellar radii.
On the plots on the right.
On the right,
Yeah.
so yeah, these are kiloseconds going upward from the simulations.
So what's the entire span of the?
I wish I knew. I grabbed this from the paper, and I had to add the t in kiloseconds because their caption is where they said that time is going upward in kiloseconds.
Okay.
I'm not the biggest fan of these plots, but they're the prettiest ones that show this effect the clearest.
Okay. The question was, so you mentioned before possible connection in the stellar cycle.
Mhm.
So is there any knowledge of the possible field?
Nope. So the only connection to like periods in a stellar cycle is that maybe this is a 20-year period. In that 20 years from now, we're gonna go to another peak in another 20 years, but this is the only notice of this because it's not optically monitored, it's not UV monitored, it's not IR monitored, so we don't know. There is a lot of plates in the Harvard Dash catalog, but I've talked to the Dash crew and it's too bright. So the algorithm can be modified, they just don't have the funding at the moment to spend weeks modifying it to get an overexposed object.
That will be fixed if we can reprocess, all the Dash data, which I'm gonna propose next year's NSF that we do.
I want to talk to you about this then.
Image subtraction rather than S extraction.
Okay,
So that would at least partly, if not totally, fix that problem.
okay.
But we got a lot of work to do on it. It's only a relatively simple part of the whole processing code.
Mhm.
It's just the photometry part.
Yeah,
Everything else is working beautifully.
okay.
And it works beautifully on most objects, but very bright things.
Yeah, when you're magnitude 2.5, it's a little hard.
Okay, let's see.
Please keep the questions coming, I'm having fun.
Nice, very nice talk. And the time coverage of for the XMM data is quite impressive.
Yep.
When you want to sample something, from 20 years, how much in your other reference sources do you have anything like other than just, a snapshot here and a snapshot there?
So that's the unfortunate thing that a lot of these are snapshots. The test data, which I show up here, is during this peak right here. I need to figure out how to actually properly process the test data, because ZetaPup is again too bright for tests. And this is just the, as an example, the pipeline data, which may not be usable because it's too bright. But the IUE and EUVE data and Hubble are 20 years separated. So maybe it caught something in this as well, showing a similar effect. Unfortunately, the Hubble data lands about right here before the huge increase. So it's a tall ask to do all of this work if it doesn't get anything, but it may also point to the need to continue monitoring this star.
Any more questions? If not, let's thank both our speakers again.
If you would like to talk with them, please contact them through their email. They're both in the neighborhood.
Stop sharing.